Hello everyone, welcome back to my channel. Today we are going to talk about center of gravity in 3 dimensions, specifically with a wire. I'll be showing you guys the problem statement soon. I hope you guys like this background I chose for this presentation. But here is the problem. So we'll get working on this problem shortly. So here's the full problem statement. A thin steel wire with a uniform cross-section is bent into the shape shown. Locate its center of gravity. So first we will have to review the centroids of some common shapes of lines. As we see here, we have some special shapes. We will be referring to this as we move on in the presentation. Here's the problem statement again. In the solution, first we will divide the overall shape into its 4 shapes, and then we will locate the centroid of each shape. Since the shape is uniform, because of the uniform cross-section and the uniform density of steel, as we will assume in this problem, the centroid is also the center of gravity of each shape. So for shape 1, we will define that as being this quarter circular arc. Shape 2 will be this diagonal line. Shape 3 will be this vertical line. And shape 4 will be this horizontal line. Next, we will be focusing on shape 1. The centroid of shape 1 is approximately there. We have to locate the centroid of each shape, as you might recall. Here are a list of special shapes. For shape 1, it is a quarter circular arc. And looking at the top, we will have to reorient that quarter circular arc to match our image shown. So the X bar in the diagram will actually be replaced with Z bar. And then that will be equal to 2R over pi. Similarly, the Y bar in the diagram will be replaced with X bar. And that will be the 2R over pi as well, where R is 2.4 meters. So Z1 bar is equal to 2R over pi, which is equal to 2 times 2.4 over pi. And then X1 bar is equal to 2R over pi, which is equal to the same thing. We also want to define the length of the semicircle, of the quarter circular arc. So the length of the quarter circular arc is equal to pi r over 2, as we see in the diagram above, right over here. So let's move on. That is in turn equal to 2.4 pi over 2. For shape 2, we locate its centroid. We magnify it because we need to. The centroid is approximately located at the half length of the diagonal. That corresponds to 1.2 meters. So x2 bar is equal to 1.2 meters, while y2 bar is equal to 0.5 meters. And why that is so is because we note over here that it is 1 meter, but we simply divide that by 2 to have 0.5. So this whole length is equal to 1.0 meters. Again, the length of the diagonal is equal to, using the Pythagoras theorem, L2 equals the square root of 2.4 squared plus 1 squared. Again, we get those lengths from observing the diagram. 2.4 and 1. Next, we will focus on shape 3. For shape 3, the centroid is pretty simple. It's just the half distance, half of 1, which is 0.5 meters. So y3 bar is 0.5 meters. L3 is equal to 1 from the diagram over here. Next, we will focus on shape 4. Shape 4 is a horizontal line. So thus, x4 bar is equal to 1.2 meters. Oh wait, sorry, that is Z4 bar because it's in the Z axis. And then L4 is simply equal to 2.4 meters. we will combine all our given information now. Remember that the centroid of a shape of a line is equal to the integral of x times the differential element of the length over the total length, while the y bar is equal to the integral of y times the differential element dl over the total length, which is L. And keep in mind that the total length, or capital L, is referring to the length of this whole wire segment. So L over all is thus equal to L1 plus L2 plus L3 plus L4, which is equal to 2.4 pi over 2 plus the square root of 2.4 squared plus 1 squared plus 1 plus 2.4. And that is in turn equal to 9.769911. So the x coordinate of the centroid for the overall shape is equal to the Riemann sum of the small x bars for each shape times the total length of the wire times the total length of that segment of wire over L over all. So over here, L over all corresponds to the capital L in the diagram above. And then we can define the y centroid and the z centroid of the overall wire in a similar way. Plugging in our given quantities, we now know that L over all is equal to 9.769911. We know that the x coordinate of the x centroid for the overall shape is equal to that. Plugging in our knowns, that is equal to x1 bar times L1 plus x2 bar times L2 over L over all. The reason why we don't have x3 bar and x4 bar, well, we do have those, but those are equal to 0. So those terms both disappear out. So plugging in our known values, we have this equation over here. You already saw how we got those sub-equations previously. And then we get the x bar of the total shape is equal to 0.909 meters. Next, we will be focusing on the y coordinate of the centroid for the whole overall shape. That is equal to y2 bar L2 plus y3 bar L3 over L over all. Plugging in our known quantities, we have that y coordinate of the centroid for the overall shape is equal to 0.1842 meters. Next, we'll be focusing on the z coordinate of the z centroid for the whole overall shape. Looking at our known quantities, we have z1 bar times L1 plus z4 bar times L4 over 9.769911. Plugging in our known quantities, we then have the z coordinate is equal to 0.884 meters. So recap of everything, the problem statement as shown, our summary, x coordinate of the centroid is 0.909 meters. Y coordinate of the centroid is 0.1842 meters, and then z coordinate of the centroid is 0.884 meters. So those are our answers. And thank you guys so much for watching this video. And I hope to see you in the next one. I hope that this helped you in your statics endeavors.